So quick recap, entropy is disorder. So it's basically this high entropy means more disorder, low entropy means less disorder. So you've got high entropy states, you've got low entropy state, you've got a clean and tidy room, that's low entropy, you've got an untidy room, that's high entropy. High entropy is easy, low entropy is difficult, it's unstable. Keeping things nice and tidy, that's difficult. Keeping things messy, that's easy. Delta S is a change of entropy. Positive means that there is a gain of entropy happening. If you break your car into pieces, or you break your bicycle into pieces, that's delta S positive. If you take the parts and make a bicycle, that's delta S negative. That's a loss of entropy. So we did all of that. We did how to predict gain of disorder or loss of disorder, gain of entropy, loss of entropy in a chemical reaction. So I stated that if you move from a solid to a liquid to a gas, that's delta S positive. Solids have low entropy. Gases have a lot of disorder. They've got high entropy. So, and then we talked about if in a reaction, the moles of gas they increase, that's a gain of disorder. You got more gases, more disorder is being created. If you're going towards less gas, that's a loss of entropy. That's delta S negative. So remember, more disorder being created, more gases being produced, that's more entropy. Less disorder being created, less gas being produced, that's less entropy. And if the states are the same, I told you to count the number of particles. If the moles increase, that's more disorder. If moles decrease, that's less disorder. Delta is negative if moles decrease. If more particles turn into lesser particles, that's you're removing disorder. And we did examples of that. Then we did, we're pretty much at the end of the topic, the first topic. The first topic was pretty small. Then I told you, how do you calculate entropy? I told you that there's a simple formula, which is that entropies of the reactants and entropies of the products would be given. So what is the entropy change? That's, you just find the difference. It's the entropy change of entropy of the product minus the entropy of the reactant. And we did some calculations using this. And this is what we had started doing in the last class, that how do you measure entropy? And I'll just briefly, last class we just had lesser time, so I'll just explain this once more. So the formula of entropy is that how much work would be produced by a certain substance, whatever the substance is, at a particular temperature. So entropy is basically the useful work that is produced by something at a particular temperature. That's the entropy change. So for example, if I have water, liquid water, and that liquid water, let's say it's at 283 kelvins, and I take it up till 400 kelvins. At 283 kelvins, that liquid water is in the form of a, so at 283 kelvins, so there's liquid water, and this is what I'm trying to do. So at 283 kelvins, that liquid water is in the form of a liquid. The disorder, the entropy is not that much. It's liquid water, and if I remove the gas particles at 283 kelvins, it's not in the form of a gas. So the piston is right at the bottom, right? Now, if I take the same 283 Kelvin liquid water and I take it up till 400 kelvins, 400 kelvins is above the boiling point of water. So the water will start to boil and it will start producing gas molecules, water vapors, steam molecules would be produced. So a lot of steam is going to be created, which is basically gas. So H2O gas is going to be created. And those water molecules, which are now in gaseous state, they are going to create a lot of disorder. A lot of gas molecules will be created, and those gas molecules are going to produce a lot of disorder. So that means delta S is positive. So that means that there's a gain of disorder that is happening, or gain of entropy that's happening. So there's a lot of gain of disorder. Now, when this happens, the gas molecules will go and they will create a lot of disorder, and they'll bump into the walls of the container, and the piston over here, the movable piston, will start moving upwards. When it starts moving upwards, work is going to be produced. So the piston starts to move upwards. Whenever disorder is created, whenever entropy is created, work is going to be produced. Imagine if no disorder had been created, then no work would have been produced. Is the idea clear that whenever disorder is created, whenever delta S is positive, whenever there's a gain of disorder, there's going to be work that's going to be produced? Is this clear to everyone? Yes or no? Is this clear?
Yes, sir.
So remember, make sure you use your space bar. That's your mic gets unmuted. Okay. And this is always true. Whenever there's disorder created, so there's going to be work produced. Imagine there's a small firecracker. If that explodes, a lot of work is produced because there's an explosion and things go flying off. So there's a lot of work that's produced. And when work is produced, it's going to be exothermic, right? The work is going to be, exothermic because it's getting produced. So work is energy. So energy getting produced, that means exothermic. Now, focus on this relationship. Focus on the signs first. If delta S is positive, there's a gain of disorder. What about work? Work would be exothermic. So the work produced would have a negative sign. So remember this, that the signs are going to be opposite. Delta is positive, disorder created, work produced. Work produced, that means exothermic, that means negative. So the energy and the entropy, they have opposite signs. Entropy change and the work produced have opposite signs, which is why in the formula, you've got a negative sign over here because these two have opposite signs. Work produced, the entropy change would be positive. So it's the work produced at a particular temperature. If I had increased the temperature even further, more work would have been produced. If I had taken it up till 600 Kelvins, there would have been more expansion, and the piston would have moved up further up, and more work would be produced. So it's the work that is produced at a particular temperature. That is what entropy change is. So is this clear? Is this formula clear to everyone?
Sir, will
Yes.
that be the change in temperature or the temperature?
Nee, what's the question?
Will it be the change of temperature?
I said this thing over here. I mean, the thing is that absolute entropies, you assume I just said that it's 283 Kelvins, right? You're moving from 283 to 400, right? Basically, you're moving from, whenever you calculate entropy change, you move from 0 Kelvins, standard entropy change. That is, you're moving from 0 Kelvins, like all the way to 0 Kelvins to 400 Kelvins, right? So the assumption is that your starting point or your reference point is 0 Kelvins. So if I want to calculate the entropy of water at 400 Kelvins, basically what I'm doing is I want to figure out that if water was at 0 Kelvins and I'm taking it up all the way to 400 Kelvins, how much work would be produced by the disorder that's created, right? So what is delta T then? It's 400 minus 0 Kelvins, right? So it's going to be 400, right? So basically our reference point is 283. I just wanted to explain this, but remember the reference point is actually 0 Kelvins. The way you measure it is you compare it with 0 Kelvins. Like how much work would be created by water or produced by water if you take it all the way from 0 Kelvins to 400 Kelvins. Alicia, is this clear?
Yes.
Okay. And remember, so entropy change of reactions. What is entropy change of reactions? Same thing. So if I burn petrol, I gave this example yesterday that in the car works on entropy change, not on enthalpy change. I explained that if I take an octane molecule, so here was an octane molecule, and I burn it, a lot of disorder is created. Why is it created? Because, one second. So if I take one octane molecule, 8 carbon dioxide and 9 water molecules are created. So there's a lot of disorder. So one molecule of octane all of a sudden turns into lots of small molecules of carbon dioxide and water molecules, right? So there's a lot of disorder created. So you add one molecule of octane. Octane is petrol, it's liquid. And all of a sudden it turned into lots of smaller, tiny molecules. And those molecules are gaseous, and they would go and bump into the walls of the container, and they would create a lot of disorder. And which is why the piston would start moving upwards. So work is going to be produced. So the piston in your car is moving. Why? Because there's a lot of disorder being created, not because of the energy. We don't care about the energy that is like if you burn petrol, a lot of heat is produced. We don't care about that heat. We're only interested in how much disorder is created, because that disorder is going to it's going to get converted into work. Is that clear? Do you guys this clear?
Yes, sir.
So this is the background of the formula. Now, about this formula, I'll just explain this, that it's not going to be a linear relation. Do you think that if I keep on increasing temperature, would entropy change increase along with it? Like if you look at this formula, if I continue to increase temperature, like let's take water for example. I mean the same water example. So about this one, if I take water as an example, if I continue to increase temperature, will the water continue to produce work due to disorder or not? Does entropy change happen in a linear way, or does it? And let's start with ice. I'm gonna take ice first. So this is ice at minus 50 degrees centigrade, right? And it's a non-linear relationship, and I'm going to plot a graph for this now. And here's the same ice, and let's say it's at minus 10 degrees centigrade. So I've increased temperature. Has the disorder increased or not? I mean, by just looking at it, is there an increase in this? Is there an increase in disorder by just looking at it? Has any work been produced? The ice looks exactly the same. I mean, let's assume that you have 2 beakers and both of them have ice. One of them has ice at minus 50, the other one has ice at minus 10. By just looking at it, both of them would look exactly the same. Is that clear? There would hardly be any entropy change. I mean, entropy would change, but there's very little increase in disorder. Very little. Is that clear?
Yes.
So we can't see it, but it's happening.
It's happening, but the reason you can't see it is because it's very little, right? There's a very small increase in disorder from minus 50 to 10. Let's say I take it to, I increase the temperature by a further 15 degrees centigrade, right? So now the temperature is 5 degrees centigrade. What do you think now? Is there going to be an abrupt change in disorder now? Now the ice is at 5 degrees centigrade. Will it be in the form of ice?
It will be a liquid.
Okay, so it will be a liquid. So basically now all of a sudden there's a large increase in disorder, right? So all of a sudden there's the disorder has increased by a big amount. So large increase So remember, for substances, disorder usually increases when you change state. Achha, when would there be a massive increase in disorder? At what temperature?
At 100?
At 100. Now there's going to be a massive increase in disorder. A lot of work is going to be produced. That's why steam engines work on steam, because the pistons will move only when the whole water would turn into. So let's say I take it to 105 degrees centigrade now. So if it's at 105, now there's massive increase in disorder. So all these particles are now flying around and they're in gaseous state. So there's a large increase in disorder. So the point is that entropy change. So this one is going to be a large increase. So remember this, that that entropy change, as you keep on increasing temperature, it's not a linear function. It doesn't, a lot of times it's not going to happen, or it's going to happen very little, right? Minus 50 to minus 10, hardly any change in disorder. Hardly any work is going to be produced by the system. But when you take it to 105, a lot of work is going to be produced by this thing. So there's a large increase in disorder. Is this point clear? This thing?
Yes.
And I'm going to plot the same thing in a graph. So let's say I have a graph and I've got entropy on one side and I've got temperature on the other axis. This axis is temperature, and I've got entropy of the system on one side. So what's happening is that hardly any increase in disorder up till 0 degrees centigrade. And then all of a sudden, not a very drastic increase, but there is an increase when it melts, right? And once it's liquid water, the disorder hardly increases. Like if you have a glass of water at 10 degrees centigrade and a glass of water at 90 degrees centigrade, both of them would look exactly the same. Hardly any difference. So up till 100, not much is happening. And remember, I also told you previously that it's gases. Gases is where the disorder is created. When something changes into gas, when you have a reaction and it changes into gas, that's when a lot of disorder is created. So a large increase in disorder will happen and will continue to happen because gases, they expand as well. So when it changes into gas, this is how the graph of entropy of water measured over time would look like. Hardly any entropy when it's ice, it increases. Almost remains constant or very slight increase when it turns into water. At 100, there's a massive increase. And gases are the only things whose disorder would increase with temperature. That's where there's going to be a relationship. Why? Because liquids don't expand, solids don't expand, the arrangement does not change. But gases, the arrangement changes because gases can expand. Okay, they have if you know kinetic particle theory, the basic structure of solids, liquids, and gases. Gases is where the particles would expand. So the arrangement would become more and more disordered. So they expand with temperature. They gain kinetic energy and they become more disordered. So they become more disordered as temperature increases. Is this idea clear? This graph, is this clear?
Yes, sir.
See, that's solid, that's liquid. Anna, is this clear? Hania, is this clear? Bilal, do you get this? Right?
Yes, sir.
Okay, so moving on, just this one graph. So make sure you keep this in mind, and At the moment, we are assuming the pressure remains constant. But obviously pressure plays a role. Like if I increase the pressure, what will happen to the disorder? Like if I sort of bring the particles all together, right? It will become less disordered, right? So at the moment, I'm just assuming that the pressure is a constant. I'm not touching pressure at the moment. Again, we're not going to discuss pressure. We're not going to go into that much detail. So let's assume the pressure is constant. So the gas will continue to expand if the pressure is constant. It's going to become more and more disordered as it gains kinetic energy. See, is this clear? So now the very last concept, the very last formula. So remember, entropy change is the work that is produced by a system at a particular temperature. And if you talk about a reaction, entropy change is basically you figure out the entropy of the products and you figure out the entropy of the reactants and you subtract the two. We did questions on that. Now, the very last thing that's known as Gibbs free energy. So now what's the Gibbs free energy? It's the total energy available to a system for useful work. So that's the total available energy. That's Gibbs free energy. So what is the total available energy? So coming back to this, let's take the octane example. I was burning petrol, right? How does a system produce work or produce energy? It produces it in two ways. One of them is heat energy. You burn petrol, a lot of heat is produced, right? So that is the enthalpy change. That's measured in kilojoules. That's you know that if you burn coal or if you burn petrol, a lot of heat is produced. So that's one thing. What's the other way that the system produces energy? And that is entropy change. When a lot of disorder is created, that disorder is going to push the system, or it's going to push the piston upwards, right? So a lot of work is going to be produced because of the disorder. So a system will produce work in two ways. One is, so delta G is basically, this is what delta G is. It's the sum of the two. It's the work that is produced due to enthalpy change. That is basically the heat that is produced. You burn petrol, heat is produced. Plus the other one, it's the work that is produced when a disorder is created. So work produced. And why is it produced? Due to delta S. Is the idea clear? Okay, that's the total energy that the system is producing. Burning petrol in a car, that is two ways in which heat or work is produced, either through entropy change or through the heat that is produced. And that is your Gibbs free energy. That's the total available energy for a system. Is this clear, this concept, this idea?
So how would we know how to find delta H and delta S?
Okay, so I mean, you know delta H, right? You did all of that in AS, right? You know how to calculate delta H. Is that clear?
Yeah.
So I'm going to write down the formula now. So you already know. I mean, there are lots of ways to figure out delta H, right? All of your AS, that's delta H, right? How do you figure out the work that is produced due to delta S? We had a formula. We wrote down a formula. I'm going to change that formula now. This was the formula, right? I'm just going to copy this one. This was how we were measuring. So this was how we were measuring entropy change. So I'm just going to turn around this formula and rewrite this. So for example, one second. Okay, so I want to figure out what is the work that is produced due to entropy change. So what is the formula now? Just rewrite this as delta Q is basically minus T times delta S. So it's the temperature multiplied by delta S. So I'm just rewriting this. And I'm going to put this delta Q over here. So this thing goes over here. So it's going to be delta H minus T delta S. And one second, let me explain this. So here's what I did. We already had this formula. We had the formula for entropy change. It's the work that is produced due to entropy change at a particular temperature, right? So we did all of this. And so if I want to figure out the work that is produced, I'm going to rewrite this. I'm going to multiply entropy change. If I know what the entropy change is, I'm going to multiply it by temperature, and that will give me delta Q. So basically, if somebody is looking for the work that's produced due to entropy change, that is minus T delta S. That's this thing. So this is the work that is produced due to delta S. Is this clear? This one? Yes or no? Is this clear?
Yes.
Sir, I need to understand this delta H that you have put here. You have written that work produced, right? But yesterday you were saying actually the heat is doing nothing for the work done in an engine, for example. So if we are writing this work produced and work produced,
I'm just
so
saying.
work produced due to delta H.
In that case,
can I explain it this way?
Yes.
Like, because the bond formation and bond breaking is taking place, which is also a work.
Yes, I mean that is enthalpy change basically. That's the heat energy.
Yes, yes. So to understand this further, can we explain it this way, that it is because the bond formation and bond breaking are taking place, and which is work? This is the reason why we are writing it work produced.
Yes, and this is let me go back to the car engine example, right? So there's work being produced in two ways, right? One is entropy change, and there's a lot of heat being produced as well, right? So there's going to be a lot of heat that would be produced as well, because burning petrol is an exothermic reaction. So a lot of heat is going to be produced as well. Now, what I stated yesterday was that the car basically works because why is the piston moving? Because of the entropy change. The heat is getting wasted.
Yes.
Like, if I want to talk about the total energy that is being produced by the system, so it's the entropy change that is producing work, and it's the heat that is also getting produced. Even though the heat is getting wasted, I don't care about that if it's getting wasted. I just want to know what is the total energy that is produced by the system. Is that clear? So I'm going to if I want to measure the total energy, the energy that is being wasted in the form of heat and the energy that is produced due to entropy change, I'll add both of them up, right? So the car is moving because of the entropy change. The heat is getting wasted. Like in over here, I just want to measure the total energy that is produced by the system. So it's the work that is produced due to heat that is being produced, and it could be consumed as well. It could be endo, or it could be exo. It depends on the system, right? And it's the work that is produced due to entropy change. This could also be negative. It could also be positive, right? It depends on what reaction you're talking about. If you take the car example, work is produced in both ways, right? So I'm just summing up both of them. Is that clear?
Yes.
And on top of that, is this clear that the work produced due to delta H, that's the heat energy that's produced, that's delta H. You already know what delta H is. It's measured in kilojoules. And delta H it's basically bonds being broken, bonds being formed. So there's heat that is either produced or consumed. It could be endo, it could be exo, right? And then there is work that's produced due to entropy change. And that I told you, the formula for that is minus T delta S. So I put in minus T delta S in its place. So is this formula clear now? This one?
Yes.
Okay, Baki clear? Is this Alicia, is this clear?
Yes.
Yes.
Okay, so that's your formula. So delta G is the total available energy that the system has or the system produces in both ways. And delta G is going to be in kilojoules per mole. That's the unit. Okay, delta H is, you already know, AS, that's kilojoules per mole as well. T would be in Kelvins, always in Kelvins, remember this. And delta S is in joules, it's joules per mole, joules per Kelvin per mole. It's the work produced at a particular temperature. And if you're talking about standard entropy, that's per mole. So the Kelvin will get cancelled with this Kelvin. So this will have, the only problem over here is that two of the values have a unit in kilojoules. The third one has a unit that's in joules. So make sure you keep the same unit. It's either all of them going to be in kilojoules or all of them should be in joules. If you're trying to calculate delta G, make sure you divide this by 1000 because entropy change is usually in joules. So you have to divide this by 1000. So make sure the units are consistent. Because the table that they're going to give you, this would always be in joules and this would always be in kilojoules. So make sure the units are consistent. Okay, so remember this thing. So either kilojoules, all of them kilojoules, or all of them in joules. You can't have one of them in joules and the other one in kilojoules. Okay, so be very wary of this. Now, let's try and measure delta G. So what would happen if delta G comes out to be negative? If the overall delta G comes out to be, if you sum up the work done that's produced due to enthalpy change and the work that is produced due to entropy change. So if delta G is less than 0, less than 0 means, it means negative, right? It means exothermic. So if it comes out to be negative, that means overall, the system has excess energy and it is producing work. So overall, the system will produce work, whether it's in the form of heat or in the form of entropy change, the system will produce work. So overall, the system produces work. And that means it's feasible. You don't have to do anything. So that means it's feasible. That means it's spontaneous. It does not need any energy. No energy is needed from the outside. So that's the overall energy. If it comes out to be negative, just like exothermic, that means the system is producing work on its own. No extra help is needed. It will do all the work on its own, and it's going to be feasible and spontaneous, and it does not need any of your help. No, Bilal, this is just the second or the third lecture. We haven't really discussed anything apart from this. Okay. We're going to do all of that. We just on the first very basic. This is just the third lecture. So we didn't discuss that. So now what if delta G is, if the overall energy of the system, delta G, comes out to be endothermic? If it comes out to be endothermic, that means greater than 0 means positive. That means it's endo. So that means the system needs energy from the outside. It needs help. It's endothermic. So it needs energy. And unless you don't give it energy, nothing is going to happen. So that means it's not spontaneous. And not feasible. Nothing will happen unless you give it energy. Is this idea clear that it's a simple idea? Overall energy of the system comes out to be exothermic. It doesn't need your help. Overall energy of the system comes out to be endothermic. It needs your help. It won't happen. The reaction will not happen. Whatever is happening is not going to happen unless you provide it energy. Is that clear?
Yes.
Okay, so the next thing is same. I mean, this is basically the last topic of this subtopic, delta G. So next thing is we're going to first try and predict based on this equation over here. When will a reaction be spontaneous and when will it not be spontaneous? So let's take this reaction. Water is a liquid and it's turning into gas. Is this spontaneous or is it not spontaneous? I mean, you've got liquid water, it's turning into gas. Is it spontaneous or is it not spontaneous?
Not spontaneous.
Well, it depends on temperature. Like, let's say at 10 degrees centigrade, is it 10? Then let me put that in Kelvins. 10 degrees centigrade is 283 Kelvins, right? At 283 Kelvins, is it spontaneous or not spontaneous? Like at 10 degrees centigrade.
Not spontaneous. Not non-spontaneous.
So it's not going to happen. Like you take a bowl of liquid water at 10 degrees centigrade, it will not turn into gas. So it's not going to be spontaneous, right? But the same reaction at, let's say, 110, that would be 383 Kelvins, right? So now is this at 110 degrees centigrade? Is this going to be spontaneous or not spontaneous? Will this happen at 110 degrees centigrade?
Spontaneous.
At 110, it's going to be spontaneous. At 1000 degrees centigrade, this would happen very fast. If the temperature is 1000, you put liquid water into that oven and it will turn into gas spontaneously. All of a sudden, it will turn into gas. So at this point, it's non-spontaneous. That means its delta G at this point is positive. It needs energy. And over here, it's spontaneous. That means the delta G at this point has turned negative. It's become exothermic all of a sudden. So let me explain using the equation now. Okay, now this is a very obvious reaction. You know that at higher temperatures, this reaction will be spontaneous. At lower temperatures, the reaction will be non-spontaneous. Okay, it's a very simple reaction. So I'm going to link it up with the equation. What is the equation that we did? The equation that we did was delta G is equal to delta H minus T times delta S, right? That was what our equation was, right? So let's do the same prediction. I mean, the same prediction, which is pretty obvious. But I'm going to make the same prediction using the equation now. What do you think is the enthalpy change of this reaction? Is it endothermic or exothermic? Guys, is this an endothermic reaction or an exothermic reaction?
Endothermic.
Yeah, that's an endothermic reaction, right? So that means delta H over here has a positive value. I mean, we don't know what the value is, but it's positive, right? Because it's an endothermic reaction. So what about entropy change? Is this delta S positive or is this delta S negative?
Will be
Positive.
negative.
Is there more disorder being created or less disorder being created?
It will be more. It will be more at higher temperature.
So that means the reaction. I said two things about the reaction. The delta H is endothermic, so that's positive, right? And the delta S is also positive, right? Because there's a gain of disorder, right? More disorder being created. Is that clear? I mean, these two things, is this clear?
Yes.
So now this was not given. We just predicted these two values based on the equation, right? So that means delta S over here is also positive. By just looking at the equation, I was able to figure out the signs of delta H and delta S. Now, one of the term, I mean, delta G is the overall, it's the sum of the two terms. Now think of this very carefully. This is positive. This thing, delta S, which is a positive value, multiplied by temperature in kelvins, it's got a negative sign in front of it. So what would that, I mean, what would this thing turn into? This will, the negative sign over here will turn this into a negative value. So one of the components is positive, while the other one, because of the negative sign present, it will actually be negative, right? So delta G is the sum of two things. One of them is positive and the other one is negative, right? I mean, this was positive, but it's got a negative sign in front of it, so it became negative, right? So for a spontaneous reaction, delta G has to be negative. So if I want to make it negative, if I want to make delta G negative, right? Which of the two terms must be bigger in size? I mean, this should be bigger and this should be smaller. Is that clear?
Yes.
If I want to make this, if I want to make delta G negative, because remember delta G negative means the reaction is going to be spontaneous. So one of the terms is positive, the other one is negative. The positive term must be small in size, the negative term must be, it should be bigger in size. How can I make it bigger? What should be the value of T? Should it be big or should it be small? If I want to make it
Big.
bigger, it should be big. So if I want to make it big, that means I need to have higher temperature, right? So this is exactly what we predicted over here. When did the value of delta G became negative? It became negative when when did the reaction became spontaneous or delta G became negative? At the higher temperature, right? And this is exactly the same thing that we predicted from the equation as well. That if I want to make delta G negative, I should have a higher temperature. If I want to make this reaction spontaneous, I should have a higher temperature. Okay, so I mean the thing was simple, but it's let me just go through this once more. The delta H, by looking at the equation, I was able to figure out that the enthalpy change is positive, and the entropy change was also positive because there's a gain of disorder that's happening. So I was able to predict that this is positive and this value, whatever the value is, I don't care, it's also positive, right? And I was able to figure out that one of the terms is positive, but because of the negative sign over here, the other term is going to turn into a negative value, right? Even though it is a positive value, but it's got a negative sign in front of it. So it will turn into a positive value. Now, delta G is the sum of a positive value and a negative value. And if I want to make it spontaneous, I need to make delta G negative somehow. And the way I can make it negative is that I keep the negative term bigger. How can I make it bigger? If I have a bigger T, that will make the negative value much bigger in size. So that means delta G would turn negative at higher temperatures. So that means it's going to become spontaneous at higher temperatures. And this is exactly what we predicted. I mean, although we were able to predict this even without knowing, I mean, everyone knows that liquid water turning into steam, that is a feasible reaction, but only at higher temperatures. It's a non-feasible reaction or a non-spontaneous reaction at lower temperatures. At lower temperatures, at -50, this will not happen. At -1000 degrees, plus 1000 degrees centigrade, this will happen very quickly. So the same thing we are able to predict from the equation over here. Did you understand this?
Yes.
I mean, we're going to practice a lot more. I mean, this one is slightly difficult, how to predict whether the reaction is going to be spontaneous or non-spontaneous. But I mean, just the basic idea. Is this clear? We'll do a lot more questions like this. We'll pick an equation and we'll try to predict, is this reaction going to happen at a higher temperature or at a lower temperature, right? So think on this. Think on this one. Where's the octane reaction? Petrol burning. The delta S is very positive. There's a lot of disorder being created, right? A lot of gas molecules being produced. And the enthalpy change is also exothermic because the heat is being produced. So that's delta H negative, right? So tell me whether this reaction is going to be spontaneous at higher temperatures or is it going to be spontaneous at lower temperatures? I mean, just use the same equation. I'm going to share the link of this board, so you have all the notes as well. Just a second. Ajay, tell me the answer to this one in the next class. That this one, take a screenshot of this one. Is this reaction going to be spontaneous at higher temperatures or lower temperatures? I'm sharing the link of the board. You can make sure you copy this before the class. And I'm going to take a snapshot. And so you're going to come up with an answer because for water, it was very easy. I mean, you know what water is. You know that it's going to boil at higher temperatures. So that was pretty obvious, but octane burning. Will petrol burn spontaneously at higher temperatures? Will this happen spontaneously at higher temperatures, or will it happen at lower temperatures? That's the question. Okay, so I'm sending a screenshot as well. And hold on a second. So let's continue next time then. Okay. And we'll do a lot more questions on this. Otherwise, we're actually done with entropy, but we'll do a lot of questions now. Okay. So, okay, everyone.
May I ask a question, sir?
Yes.
So you're saying in the formula that you have written, delta G is equals to delta H minus T delta S. So as we are increasing the temperature, we are also increasing delta S, right? And as we are increasing this value, whether it is temperature or it is delta S, automatically delta G is also increasing.
As we are doing what? As we are?
Increasing either temperature or in turn, delta S is also increasing, right?
Yes.
So this is how the negative side value is increasing. So that will cause delta G a greater negative value.
Yes.
So can't we say that these are directly proportional?
But it depends on the sign of delta S, right? Because the entropy change could be positive as well. It could be negative. It could be, because it depends on the reaction. Sometimes disorder is being created. Sometimes it's not being created, right? So
okay. So, but can't we say that at the temperature rise, delta S will increase?
but it can decrease as well, right? Because if it's a negative value, it will become more negative, right? If it's a positive value, it will become more positive. If delta S is positive, you're multiplying it by temperature, so obviously it's going to increase. But if it's negative,
right?
If delta S is negative, then it will continue to decrease, right?
Right, because that's going to be plus then, minus and minus, then and that's going to be plus. The formula sign will change.
Exactly.
Okay, so we can't straight away say it is directly proportional.
It's not,
that will depend on this equation or the reaction that we are dealing with.
And it will depend on the sign of delta S, whether it's positive or negative.
Right.
So we'll do more.
The delta S can be positive or can even be negative.
Yes,
okay,
exactly.
Thank you, sir. Thank you.
We'll do more questions. We'll do a lot more questions in the next class on the same thing. Okay. So, okay, everyone, take care. Allah Hafiz.
Allah Hafiz.